In part 2, we're looking at populations, samples, and probability. So in general, all we're doing in inferential statistics is addressing probabilities, kind of like when we make decisions based on these answers. What are the odds that the coin flip will result in heads? Or what are the chances that it will rain today? Or how likely is it that the cattle will be in the road when I'm driving to work today? We do this mentally all the time, and so we make decisions based on these odds. So maybe we want to do a fair chance to choose someone. We know the odds are equal, so we flip coins to make those decisions where we want equal odds. We might look at the sky and make an educated guess as to whether to bring rain gear. We might look at our past experience. How often are the cows in the road, and decide whether to leave early for work. So we do this all the time. In inferential statistics, we are just calculating the odds of getting a similar result again in the population, and then deciding whether our treatment is worthwhile. But we're just calculating odds. For example, we might conclude after a statistical test, there's an excellent chance that if we use this treatment again in another group, it will be effective. Or it's highly likely this outcome can be attributed to the medicine. Or this treatment isn't likely to be effective in the population. And so in order to make these claims, we usually set very high standards. Like we say, we're not going to make this claim unless we're 95% or even 99% certain. So in the basics, we talk about expected relative frequency, what we would expect if we do an action many times. The outcome are all the possibilities if we conduct the experiment. So we figure out how many possible outcomes. In a coin toss, there are 2, heads or tails. In a dice roll, there are 6 possible outcomes. We could get a 1, a 2, a 3, a 4, a 5, a 6. And if we have a deck of cards and we're looking at how many suits there are, well, there are 4 suits: hearts, spades, diamonds, clubs, so 4 possible outcomes. And we compare that with, using this formula, probability P, possible outcomes after all outcomes. And this lowercase p is important. I use it all the time, so I'll write it in there. So what is the probability of getting heads in a coin toss? Well, we take the heads as 1 possibility, so the numerator is 1, 2 possible outcomes, denominator is 2, and the formula is just 1 over 2, or 0.5. Usually we would express it as P equals 0.5 or 50%. The odds of rolling a 5 or a 6 with 1 dice, well, what are the things that we're looking for? Either a 5 or a 6. There are 2 of them, so the numerator is 2. The denominator, 6 possible outcomes. We already established that. The numbers 1 through 6. And so the odds are 2 out of 6, or 1 out of 3, or 0.33. The probability is 0.33 or 33%. And likewise, the odds of drawing a face card from a deck, well, there are 12 face cards in the deck, 52 cards in total. And so 12 divided by 52, we get the probability of drawing a face card as 0.23, 23%. I'm not going to do these examples because I think we have enough clarity on how we calculate these odds. So in conclusion, descriptive statistics give us information about the individuals in the sample. Excuse me. If the sample is carefully chosen, we can generalize back to the population. Populations are all the members of the subgroup of interest, and samples are just subsets of that population. Random sampling is the only way to be able to infer to population. All other sampling methods produce bias. Inferential statistics allow us to generalize to a population going beyond the descriptive statistics. And we represent population parameters by Greek letters with lowercase mu looking like this, referring to the population mean, and lowercase sigma referring to the population standard deviation. When we're talking about the sample, in this class we use M for mean and SD for standard deviation at this time. In other classes you may have seen that X bar. For mean, it's the same thing.